Good day and welcome to my YouTube channel. I am Arthur Francis Digan. Today we're going to be dealing with alkanols, that is chemistry. Another name for it is called alcohols. We know a whole lot of persons have different views when it comes to that name, alcohols. They have their various definitions as to what is alcohols. Some of them will say gin is alcohol, but wine is not alcohol. That contradiction is there, which we're going to address it some other time or in another class in a topic called alcoholism. But today, alcohols are any compound that have the hydroxy group, that's the OH group attached to its carbon atom in an sp3 hybridized manner. So let's go through. There are a whole lot of other stuff we're going to look into. I say again, alcohol is a class of organic compounds with a hydroxy functional group attached to an sp3 hybridized carbon atom. So that is what we're dealing with directly. So the general structural formula for monohydrate alcohols is the CnH2n plus 1O. So this is the general molecular formula which we are going to use to determine all the members of the alcohol family which we'll be dealing with. So that means that if a compound, the N here is for the numbers, B1, 2, 3, methanol, ethanol, propanol, butanol, as the case may be. So let's say if it is 4, which is butanol, then I want to know how many carbon and hydrogen there are in butanol. I'll be having C4H2 times 4 plus 1 times 4 plus 1 OH, which is C4H2 times 4 is 8 plus 1, 9 OH. And the structure therein becomes 1, 2, 3, 4. That's for the carbon atom. Hydrogen, we have 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, and the OH here is 1. So this becomes the structural formula for the compound butanol, or butan 1 or 1 butanol, as the case may be. So this trend continues if you, no matter the compound or the number which you're dealing with, pentanol, hexanol, heptanol, octanol, decanol, anyone. All you need to do is to use the general molecular formula to know the exact number of hydrogen therein, and you proceed. So we're going to look at the classification of alcohols. We have the primary, the secondary, and the tertiary alcohols. The primary alcohols, we have two classifications, but the one we're dealing with for the monohydrate alcohols, we say a primary alcohol is that alcohol where the carbon carrying the OH group is attached to one carbon atom or none in the system. What do I mean by that? So the first one here we say primary alcohol. The carbon carrying the OH group, this is the carbon, is attached to either one other carbon atom. This is the carbon carrying OH group, it's attached to just one other carbon atom, which is this. So this is the primary alcohol. This carbon carrying the OH group must be attached to one other carbon atom or non-carbon atom. What do I mean by that? Or I can have this. This is my carbon carrying the OH group. So if it's attached to non-carbon atom, which means it will be hydrogen. So this is CH3OH. This gives us what? Methanol. Then this one, which is also a primary primary alcohol, is attached to one carbon atom, and this is ethanol. So it can be butanol, as the case may be, and the position of the OH defines whether it is primary or secondary or tertiary. For example, if I have this OH here, this OH, this is the carbon carrying the OH, it's attached to just one carbon atom. So this is also what? A primary alcohol. So it doesn't matter. If this OH were to be here, it will no longer be primary because this carbon carrying the OH will be attached to two carbon atoms. So in that sense, it is not primary alcohol. But now, the carbon carrying the OH is attached to one other carbon atom, and that is primary alcohol. So let's talk about secondary alcohol. In secondary alcohol, the carbon carrying the OH group is attached to two carbon atoms. Secondary alcohol. This is the carbon carrying the OH group. Let's put our OH group here. It's attached to two other carbon atoms. So this could be my hydrogen. So this is the secondary alcohol because this is the carbon carrying the OH group, which is the functional group. This carbon is attached to two other carbon atoms. And this is 2-propanol or propan-2-ol, as the case may be. So this is what secondary. Then in tertiary alcohol, the carbon carrying the OH group, if this is the OH group, is attached to three other carbon atoms. 1, 2, and 3. So I can put my CH3 here. So this becomes 2-methyl-propan-2-ol. So this is a tertiary word, alcohol. So you don't forget it because in the classes of carbon which we have defined, the primary, secondary, and tertiary carbon in our previous video, I think that would be organic chemistry 2 or 1, as the case may be. We talked about the classes, which is important because we do not have to go in details discussing about this because we've talked about it earlier on. If you still remember that, you can apply the knowledge here and we'll continue. So let's look at the second classification, which is based on the number of hydroxy groups per molecule. Okay, this is for the monohydric alcohols, but this time around we're looking at the classification based on the number of what? Hydroxy groups. So we'll talk about the monohydric alcohols. We say these alcohols contain one hydroxy group in the molecule. So the classification, the first one is monohydric. So mono in chemistry is 1. The second classification is based on what? The number of what? Hydroxy groups attached to a molecule. So we first talked about the monohydric what? Alcohols, where there is just one OH group. So we can have something like this, and we have just one OH group, and that is 1-propanol. It can be 1-butanol. It can be anything. So in the, let's take the primary alcohols. Okay, I've talked about this one. So the first one here, which is, the one I have here is 2-butanol, that is 1-propanol. Let me give you another example. It can be this. 1, 2, 3, 4. And your OH is here. Remember, carbon is tetravalent. Means there are hydrogen bond positions here, even when I don't put them. If you have been following our videos by now, you should be used to the fact that even when there are no hydrogens, you know what we're dealing with. Here, there is just one OH group. It doesn't matter the position. So it is in the second carbon. So 1, 2, 3, 4, the parent chain is what? Butane. So, and the OH is in the second carbon atom, so we call it butan-2-ol or 2-butanol. As the case may be, there are two ways which we can name them. So we can also have any one you want, 1-pentanol or 2-hexanol, as the case may be. So let's look at the classification based on dihydric alcohols, which means there are two hydroxy groups in a compound. There are two hydroxy groups. We say dihydric alcohol. Let's take the simplest one. This is the first one. I have my OH here. I have my OH here. This is ethane 1,2-diol. Now, when there is one ol, we call it mono. But when there are two ol, it's called di in chemistry. That becomes what? Diol. So this is ethane or 1,2-ethane-diol or ethane 1,2-diol. So that has to do with the number of what? Hydroxy groups attached. So we can take another example here. 1, 2, 3, 4. I have my OH here. I have my OH here. This is 1,2 propane diol. The OH is in the position 1 and 2 of propane. Sorry, this is butane. This is butane 1,2 diol because we have 2 of these. It can be butane 1,4 diol. If the position is here, dihydric, we still have 2 hydroxy groups. So this becomes butane 1,4 diol. If it is in the middle here, it is butane 1,3 diol. So this is classification based on the number of hydroxy groups in the compound. So let's move further and take more. Trihydric alcohols means that there are 3 hydroxy groups in a molecule. There are 3 hydroxy groups. So let's take this. 1, 2, 3. I have my OH here, OH here, OH here. This is propane 1, 2, 3 triol. Because there are 3 hydroxy groups, so it is triol. So I can easily put it as propane 1, 2, 3 triol. And if I want to get another example, I can put my C here. This is butane 1, 2, 3 triol. If I put another one, pentane 1, 2, 3 triol, I can change the positions of the OH. So it can be here. Okay. Okay, let's take it here, OH. This is 1, 2, 3, 4, 5, pentane. So that this becomes pentane 1, 3, 4 triol. So we check the number of locants. We talked about the locant, the lowest possible number. If this is 2, 3, 5, this is higher, so it goes this way. 1, 3, 4. So this is pentan or pentane 1, 3, 4 triol. So let's take polyhydric alcohols. We are talking about classification based on the number of hydroxy groups, where we've talked about the monohydric, which contains 1 hydroxy group. Dihydric alcohol, it contains 2 hydroxy groups. Trihydric, which we just discussed, contains 3 hydroxy groups. Polyhydric contains 4 and above. All right. So if it is 4 and above, I can easily take this one, put my OH here. This is polyhydric. 1, 2, 3, 4. So this is 1, 2, 3, 4, 5 pentane 1, 2, 3, 4 tetraol. Pentane 1, 2, 3, 4 tetraol. Means there are 4. Tetra means 4. There are 4 hydroxy groups. So we also have the mannitol, which gives us 6 carbon atoms. It's called a mannitol. 1, 2, 3, 4, 5, 6. Contains OH here, OH, OH. This is mannitol. Hydrogen, you should know that your hydrogens are here all around. Even if we do not put them, you should know that. So that is the classification based on the number of hydroxy groups. Now, the name of an alcohol is obtained by replacing the terminal E in the alkane. Remember, we have alkanes where it ends with ANE. So we replace the terminal E in the ANE. in the corresponding parent hydrocarbon with OL. So that becomes the alcohol. So let's look at the procedure for naming alcohols. So, like I've been naming these ones, 2-propanol or 1,2 that and that. Let's look at the procedure so we'll be able to understand the principles involved in naming them. Now, first, number one, we say the parent structure is the longest continuous chain of carbon atoms. Remember, we have always had the parent structure to have the longest parent chain in all our discussions. In alkanes, and alkynes, the parent must be, first of all, the longest. Now, which must include a carbon bonded to the hydroxy group. So the hydroxy group must be included in that parent structure, otherwise it is not the parent structure. The number of carbon atoms determines the parent name. So let's take ethanol or 2-propanol. 1, 2, this is ethanol, or 1, 2, 3, this is 2-propanol. So this is our parent chain, the propane backbone, and the same thing here, a cane backbone for the second one. With ethanol having 2 carbon atoms and 2-propanol having 3 carbon atoms, so that is the longest. So that is our parent chain. The second rule says the parent chain is numbered such that the carbon atom bonded to the hydroxy group has the lowest possible number. So it has always been that the number of hydroxy group on the position, we check the positions of their locant. The lowest possible number of locant give us our parent chain, and this time around we take it from the hydroxy group. So the lowest possible side must be from that of the hydroxy group. That gives us our parent chain, right? What am I saying in essence is this. If I have something like this, my OH is here. My parent chain, of course, is 1, 2, 3, 4, 5 is pentane. But in the course of my naming, I cannot say 1, 2, 3, 4. I cannot say 4 hydroxyl pentane or 4 pentanol. Alright, that would be wrong. It will be from this direction, which is the lowest possible side. Here is 2 pentanol and not 4 pentanol. So the position of the OH must be the lowest possible when you count your parent chain and not the other way. So the positions of the locant here is 2 from this direction and 4 from this direction. 4 is higher than 2. So we must start the numbering from this direction, which is 2 pentanol. Note the position of a functional group has preference over the positions of multiple bond or substituent. So when there are double bond in it, we always give credence to the positions of the functional group, which is the OH, first, before we consider that of the double or triple bond. 3. In naming, the positions of the functional group and substituent are specified. So you must tell us whether it is in 2 or it is in 3, as the case may be. So, for example, this is 2 pentanol. This is ethanol, as the case may be. But this 2 pentanol shows you that the OH is in position 2. If I should put it here, which is 3 pentanol, it shows that the position of the OH is defined is in position 3. Otherwise, one wouldn't know how to write the structure. If I say pentanol, without telling you the position of the OH group, you will not know where to fix it. So let's take a practical example. 1, 2, 3, 4, 5. The structure here is 5. Of course, you know that these are all CH3. They are substituents. So this is what we have. We now begin. Now, this is our functional group. So this will be named last. So if I want to name this, I first of all look at what is my parent chain. 1, 2, 3, 4, 5. Okay, this is my parent chain. This and this are substituents. And they are methyl. So now I have here to my position 1, 2, 3, 4, and 5. So this is 3,4 dimethyl 2-pentanol. That's it. Let me write it out. 3,4 dimethyl 2, OH is in position 2, 5-pentanol. Or 3,4 dimethyl pentan-2-ol. It's another way, if you like it that way, pentan-2-ol. Methyl pentan-2-ol. So either way, we can still go with it. 3,4 dimethyl pentan-2-ol or 3,4 dimethyl 2-pentanol. So any of that. Now, the fourth rule says, in an unsaturated alcohol, unsaturated means it has a double bond in it. The parent carbon chain must contain both the hydroxy group and the multiple bonded carbon atoms. In numbering, preference is given to the functional group first, which is the OH group, then the multiple bond, and finally the substituent. So, we will have 1, 2, 3. Let's take an example here. So now we have a double bond. We have a substituent, and we have our functional group. So we want to name it, first of all, our parent chain here. Normally, if you want to count, you say 1, 2, 3, 4. Butane kind of parent chain, but according to the law, it must contain the double bond. The parent chain must take in the double bond, so preference is given to the double bond before this. So because of that, we go straight and not this way. So that is become 1, 2, 3. So if this is it, now we have in 2, this becomes then a substituent. If that is a substituent, now this is 2-ethyl propane, but 2-ethyl prop, 2-ene, this ene tells you that there is a double bond. 2-ene, 1-ol. Now there is a double bond in carbon 2, and there is an alcohol group, a hydroxy group in carbon 1. So this is 2-ethyl prop 2-ene. There is a double bond, an ene group, and 1-ol. So this becomes the name of this. So we should don't forget that. Let's take another one. We have 1, 2, 3, 4. Here is a double bond, a triple bond. This is my OH. Let's check if that is all. 1, 2, 3, 4. Okay, now, since our OH takes precedence over this, so this is our position 1, position 2, position 3, and position 4. This is both the back chain, the backbone being the butane chain. So we have both 3 and this is YN. 3-ine, 1-ol. This becomes the name of this compound. Now, and the last rule, say if the molecule is polyhydric, the parent chain must contain as many hydroxy groups as possible. It is then named as E-diol, E-triol, etc. For instance, let's take, I think I've named this earlier on, but let's go with it again. It says it must be E-diol. For example, this is ethane. Ethane 1,2-diol. 1,2-diol. Or 1,2-ethane diol. So this is what they were trying to define, this particular one, exactly this. So let's say if we have two OH group in naming it, we end it with E-diol or E-triol or E-tetriol. What does that mean? Like here we have the OH in position 1 and 2. So I say 1,2-ethane. This is the E. E-diol. That's what I mean. Let me read it again so you understand better. It says that if the molecule is polyhydric, the parent chain must contain as many hydroxyl groups as possible. It is then named as E-diol or E-triol, for instance, which is this 1,2-ethane diol. And let me take another one. 1, 2, 3, 4. Okay. Yeah, we start our naming from here. Because OH 1, 2, so it will be lower than from this other direction, which is 1, 3. So if that is true, I have my 1, 2, 3, 4. Now I want to name it. I have 1, 2, 3, 4 methyl. 1, 2, 3, 4. Butane. 1, 2, 4 triol. Or 1, 2, okay, yeah, let's go with that one. 4 methyl, I want to start from here. So I have my 4 methyl butane. One, 2, 4 triol. We take more. Okay. So that's how we go. 4 methyl, we move. So first, you have to count to be certain about your parent chain. You count them 1, 2, 3, 4. And the last carbon atom we have is CH3. Oh, sorry. This continues. It doesn't stop here. This is the last carbon atom. It is not a substituent. That was a mistake. So this is 4 and this will be 5. You have to look at it carefully. We can easily make mistakes. So this continues as a parent chain 1 to 5. So it is not a substituent. If it were to be in the second to the last carbon, it is a substituent, but it is not being the last. So from there, it means the name changes. So this is not 4-methyl. So it becomes pentane. In short, let me just write it again. It's either called 1, 2, 3, 4, 5, which is pentane. 1, 2, 4 triol, or 1, 2, 4 pentane triol. I think I will go with this one, pentane 1, 2, 4 triol. Better than pentane 1, 2, 4 triol. So take note of this last CH3, the carbon atom. The terminal carbon cannot be a substituent. We can easily make mistakes. So let's be watchful. So we are going to take a series of other examples so that we know where we are. Now we look at isomerism of alkanols. What is isomerism? A phenomenon whereby compounds having the same molecular formula but have different structural arrangement. This chemistry exists in alcohols too, or alkanols. To be able to have the same molecular formula, but we have different structures from there. So let's take an example. C3H8O. We have C3H8O. So we have this as our molecular formula. Let's see how can we write it to have two structural arrangements from here. So I have my 1, 2, 3, exact 1, 2, 3. Okay, this is 1 hydrogen, 2 hydrogen, 3 hydrogen, 4 hydrogen, 5 hydrogen, 6 hydrogen, 7 hydrogen. The last hydrogen gives us our 8th hydrogen. So we can also have this as OH here, 1 hydrogen, 2, 3, 4, 5, 6, 7, 8. So that's it. So this one molecular formula will be able to get two structural arrangement, which is this and this. This is 2 propanol, and this is 1 propanol. Propanol, and this is 1 propanol. So that is isomerism, where compounds having the same molecular formula, but they have two different structures. That's it. So we take another example of isomerism, C4H10O. So let's see. We can have 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. I will place that. So now, if I have my OH here, it's 1 butanol. If I have my OH here, it's 2 butanol. If I have my CH3 here, and OH here becomes 2-methyl propan 2-ol, or 2-methyl 2-propanol. So in all of them, CH3 hydrogen 6, 9 plus 1, 10 hydrogen with 1 oxygen. 3, 6, 7, 8, 9, 10 hydrogen, 1 oxygen. 3, 4, 5, 6, 7, 8, 9, 10 hydrogen, 1 oxygen. So all these are isomers of this compound. So isomerism again is a phenomenon whereby compounds having the same molecular formula, but their structures are different. We can do this on and we'll continue. So let's take some questions and just solve them directly. They say, write the structural formula and the IUPAC names of 3 isomeric alkanols with the molecular formula of C5H12O that are secondary alkanols. So this is technical. Well, let's start. Now let's read this again. Write the structural formula. So we're going to write the structural formula and their IUPAC names and their names of 3 isomeric alkanols. So this has been given to us. We should form isomers with the 3 isomers from that compound with their molecular formula, which has been given here, that are secondary alkanols. So there is the direction that the isomers, the 3 isomers which we want to form, all of them should be what? Secondary alkanols. So aside that, it is not allowed. So let's start. So the first one, 1, 2, 3, 4, 5. If I have my OH here, it's second. Okay, that's 1, 2, 3, 4, 5. If I have another 1, 2, 3, 4, 5. If I have my OH here, it's also second. And if I have this again, I will name them. Let's say we should name 1, 2, 3, 4. 5 carbon atom. And I have my OH here. So I don't need to put it there. Put my OH here. This is primary, sorry. This is secondary. They say 3 of them from this. We should give their name. Yes, their structures have been given, but we should give their name. So this is 1, 2, 3, 4, 5. This is 2 pentanol. Yes, this is 3 pentanol. 2 pentanol, 3 pentanol. Here, 1, 2, 3, 3 methyl butan 2-ol. 3 methyl butan 2-ol, or 3 methyl 2 butanol. This one is 2 pentanol. This one is 3 pentanol. But the focus is that all of these are all secondary alcohols. They are all secondary alcohols. Because the carbon carrying the OH group is attached to 2 carbon, 2 carbon, 2 carbon. So they are all secondary alcohols. Now, let's move on to another question. We are answering questions now. Next question says, write the structure and the IUPAC name. The structure and the IUPAC name of an optically active alkanol, which is isomeric with pentanol. Okay, pentanol is okay. C2, 3, 4, 5. 1, 2, 3, 4, 5. This is our OH. Hydrogen, hydrogen, hydrogen. So first, this is our pentanol. But they say we should write, let me read it again. Write the structure and the IUPAC name of an optically active alkanol. What is an optically active compound? Is that compound which has a carrier center, which means it can rotate plane polarized light to either the left or right. Okay, the level rotatory and the dextro rotatory. So we have to use this and form that compound. Now, for a compound to be carrier, which is optically active, it means that carbon is bonded to 3 different substituents. So let's take, this is carbon 1 in the middle. We have OH, they say, which is isomeric to pentanol. So we have OH, we have CH3, we have hydrogen, and we have 1, 2, 3, 4, and 5. Okay, now let's look at it. Is this isomeric to this? Let's finish. Hydrogen, 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 hydrogen. This carbon is my carrier carbon. This carbon is bonded to a methyl, a hydrogen group, an hydrogen, and a propyl. So this carbon has 3 different substituents. It is a carrier carbon, which means it is optically active. Now, what we want to find out, is it isomeric with this pentanol? If it is isomeric, then we name it, we move. So now we have one carbon, we have 1, 2, 3, 4, 5 carbon. 1, 2, 3, 4, 5 carbon. We have one OH group, we have one OH group. We have 3 hydrogen, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's isomeric. So this is the structure they asked us to write, which is isomeric with pentanol, but is optically active. So now what's the name? This is 2-pentanol. So this is 2-pentanol. It is isomeric. Let's move on. We are asked to give the IUPAC name of the following compounds. Let's take the compounds. 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5. OH in the second, CH3 there. Okay, that's the first one. They say we should give it a name. What's the